Welcome! In this Choose Your Own Adventure lab, I chose to observe the motion between two objects of different masses that are dropped stacked on top of each other, in this case a tennis ball on top of a basketball, in order to predict how high the tennis ball will go after the balls collide and bounce back up. In order to achieve this, three physics principles were implemented: Newton's second law, the conservation of momentum, and the energy principle, along with data describing the ball's motion obtained from Tracker. Using all of these things, I was able to predict the tennis ball's height to be 3.4 meters and the observed height to be 3.07 meters. As seen in the Tracker video, the basketball was held 1.271 meters off the ground, while the tennis ball was held 1.58 meters above the ground, while the origin of the axes was the point on the ground that the basketball hits on its first fall. The path of the tennis ball is red, while the path of the basketball is blue. The two were then dropped at the same time and fell at the same rate, as expected due to the conservation of momentum. However, as soon as the basketball hit the ground and bounced back up, thus hitting the tennis ball is shot upward at a much greater velocity due to the exchange of energy per the energy principle. Newton's second law says that the sum of all of the forces on an object equals the mass times the acceleration. This can then be expanded to calculate the velocity as v final equals v initial plus the net of the forces divided by the masses times delta t, as well as this position as position final equals position initial plus velocity times delta t. Newton's second law is used to predict the velocity and position of both of the balls at different times during the fall, collision, and the rise. Momentum is equal to mass times velocity, and the conservation of momentum states that the initial momentum is equal to the final momentum. This principle can then be expanded to calculate velocity as v final is equal to v initial times 2 times the mass of the tennis ball minus the mass of the basketball, all divided by the mass of the system, so the mass of the basketball plus the mass of the tennis ball. This calculates the velocity of the tennis ball immediately after it collides with the basketball. The third physics principle used is the energy principle. This states that the change in energy is equal to work plus heat, which is equal to the change in kinetic energy plus the change in potential energy. Our system does not have any transfer of heat between the system and the surroundings, nor any potential energy, so the energy principle gives us work equal to the change in kinetic energy, which is also force times change in position equals change in kinetic energy. The energy principle is used to show the change in energy as the ball travels together, then collide, and then travel upward at different velocities. Start it. The tennis ball has a mass of 0.057 kilograms, a radius of 0.067 meters, an initial velocity of 0 meters per second, and an initial position of 1.58 meters off of the ground. The initial position of the tennis ball was calculated by taking the sum of the initial position of the basketball along with the radius of the basketball and the radius of the tennis ball. The basketball has a mass of 0.624 kilograms, a radius of 0.2426 meters, an initial velocity of 0 meters per second, and an initial position of 1.271 meters off of the ground. I also added t final, the time it took for the tennis ball to reach its maximum height, which was 1.168 seconds. On the left is the final position of the tennis ball compared to the position of the basketball when the tennis ball is at its apex. As seen, the tennis ball has a much greater trajectory than the basketball. On the right is a graph describing the energy of the system. The red line is the change in translational energy of the basketball, the blue line is the change in kinetic energy of the tennis ball, and the green line is the total change in energy. Although the Python code did a fairly accurate job of modeling the system's motion, there was still some error. Reasons for this include the angle at which the ball was dropped, the fact that both balls did not have smooth surfaces, as well as the way the balls were positioned in Tracker. Especially in the case of the tennis ball, because the change in velocity was so severe and the ball was fairly small, oftentimes it was not clear where the true center of mass was on the frame. From Tracker, we know our predicted height to be 3.44 meters and our observed height to be 3.07 meters. The percent error between these two calculations was 9.7%. Although the predicted results do not match perfectly with the observed results, it is still safe to say that it is possible to predict the height of an object after it collides with another object. Thanks for watching my video!